Welcome to an in-depth look at the 8 fundamental gas laws that govern the behavior of gases. Gas laws describe the relationship between key variables: pressure, volume, temperature, and the amount of gas. These laws relate pressure, volume, temperature, and the amount of gas for what are known as ideal gases. Ideal gases are hypothetical, meaning their particles have no volume and no attractive forces between them. Our first classical law is Boyle's law, which explores the inverse relationship between pressure and volume. When temperature and the amount of gas are kept constant, pressure is inversely proportional to volume. Compress a gas, and the pressure increases. A perfect everyday example is pushing down a syringe plunger. Volume decreases, and pressure inside increases. Next is Charles's law, linking volume and temperature. At constant pressure and amount of gas, volume is directly proportional to temperature. Remember, all temperature calculations must use Kelvin. Think about a balloon. It shrinks in a freezer because the colder particles move slower and take up less space. Gay-Lussac's law describes how pressure responds to temperature changes. When volume is constant, heating a gas increases its pressure because the faster-moving particles collide with the container walls harder and more frequently. This is why heating a sealed aerosol can is extremely dangerous, as the pressure builds up without room to expand. Avogadro's law states that volume is directly proportional to the amount of gas or moles when pressure and temperature are constant. This explains why inflating a tire increases its volume. The combined gas law merges Boyle, Charles, and Gay-Lussac into one equation for when pressure, volume, and temperature all change, provided the amount of gas remains constant. The ideal gas law is the most powerful equation, linking all 4 variables. Pressure times volume equals moles times the gas constant R times temperature. Next, we have Dalton's law, which applies to mixtures of gases. Dalton's law of partial pressures states that the total pressure of a gas mixture is simply the sum of the partial pressures of each individual gas. This law applies to everyday examples like the air we breathe, which is a mixture of gases like oxygen, nitrogen, and carbon dioxide. Finally, Graham's law explains that lighter gases effuse or diffuse faster than heavier ones. That's why helium escapes a balloon much quicker than air does. Understanding these 8 laws is essential for predicting and describing how gases behave under various conditions.